Okay, we saw in section 4.9 that we can take antiderivatives of different functions, where if they give us a rate of change or derivative, we are able to take the antiderivative to come up with the previous function. So if they gave us a velocity, we were able to find the position function. Or if they gave us the acceleration, we were able to find the velocity function. But what happens if they don't give us a function and maybe we just have a graph? Well, antiderivatives can also be used to help us find the area underneath the curve, or vice versa. Finding the area underneath the curve is the same thing as finding my antiderivative. And so many functions don't have an antiderivative that we can easily find, so we can approximate the area underneath that curve by taking it and separating it into a whole bunch of different rectangles. It's called a Riemann sum. So the method of approximating area underneath the curve by dividing it into rectangles is called a Riemann sum, which is going to help us approximate the area, which is then going to give us an approximate antiderivative value. Now, the more rectangles you have, the more accurate your approximation is going to be. And so I can use the area of a rectangle, base times height, and I can do that a couple different times, add them together, and approximate the area. But the more rectangles I have, the better my approximation is going to be. And so as the number of rectangles gets bigger and bigger and bigger as it approaches infinity, then we end up getting an exact area underneath the curve. So we've got to be able to take an area underneath the curve and approximate it using rectangles. So we've got to be able to figure out what the base or the width of all my little rectangles are and the height of all my little rectangles. And so depending on how many rectangles you're going to use and the interval you're in, we've got to figure out the width of your rectangles. So if you have an interval from A to B and you want to divide it by a certain number of rectangles, we can figure out the widths of all my rectangles. We're going to call it delta x, that's the change in x, by taking my interval. So let's say I wanted an interval from, I don't know, we have a function here, we want to go from 1 to 9, and I want to find the area underneath this curve, and I can separate it into a whole bunch of different rectangles. Well, if I go from 1 to 9, that's a total of 8 units. Let's say I wanted to divide that into 4 different rectangles. Well, then I can say that each of my little rectangles is going to be 2 wide. The base or my delta x or my width of my rectangles are going to be 2 units wide. Then we would just have to find the height and do base times height plus base times height plus base times height plus base times height. And that would give us an approximate area underneath that curve. When we're doing rectangles, we can do a couple different things. We can use left endpoints, right endpoints, or midpoints, meaning the left endpoint of my rectangle is what's going to touch my function, or the right endpoint of my rectangles are going to touch my function, or the midpoint of my rectangles are the ones that are going to be the same value as my function. Let's do an example of each in example number 1 here. It says here to find the area of the region bounded by the graph of the function and the x-axis over the given interval. So they give me a function y equals x squared, and so I kind of sketched a graph, and I know it was going to be a parabola opening up at 0, 0. And I know I want to go from 0 to 1, and I want to find the area underneath the curve, so the little gray shaded region. And it says here that we want to use 4 different rectangles. So if I know that I want to separate it and make 4 different rectangles, let's figure out how wide each of our rectangles is going to be. Let's find our delta x. And so if my interval is from 0 to 1, I know there's a total of 1 unit. If I want to divide it into 4 different rectangles, well then I know that each of my rectangles is going to be a 4th wide. And so the first rectangle is going to be over at 1/4. Then the next rectangle is going to be another 1/4 wide. So I have 1/4, I have 2/4, I have 3/4, I have 4/4. So I know exactly on my x-axis where each of those rectangles are going to be. Okay? Example number 1a asks us to use right endpoints of our rectangles. So we've got to be able to draw these rectangles where our right endpoint touches my function. So I'm going to start over here. I'm going to start over here, and I'm going to take the right, I'm going to follow it up to my function, follow it over, and make my rectangle. I'm going to start at the next one from the right, follow it up to my function, and follow it over. I'm going to take the next rectangle from the right, follow it up and over, and those will be my 4 rectangles. Again, you notice that the right endpoint of each of my rectangles is the endpoint that's touching my function. If you notice on this graph, because of its shape and because I'm doing right endpoints, do you notice that all my rectangles are going to be above my graph? So when I go to do base times height, base times height, base times height, base times height, and add them together, my answer is actually going to be an overestimate. It's going to be above the actual area because of the shape of my graph, because it's increasing, and my rectangles are being, my right endpoints are being used on my rectangles. All right, so we have to do our area of these four rectangles, base times height, base times height, base times height. If you notice that the base, the width of each of these rectangles are all going to be the same, right? They're all going to be 1/4. And so if all the bases are 1/4, can I GCF out that 1/4? And so then all I have to do is figure out the height of these four different rectangles. Now I want you to look carefully at this graph. You notice that the height of the first rectangle corresponds to the x value at 1/4. The height, the y value of my second rectangle corresponds to x equals 1/2. The y value of my third rectangle corresponds to x equals 3/4. And the y value, the height of my fourth rectangle, corresponds to x equals 1. So I should be able to then use my function, and I should be able to figure out the y value when x is 1/4, the y value when x is 1/2, the y value when x is 3/4, and the y value when x is 1 by plugging those values in. When I plugged in a 1/4 and I squared it, I got 1/16. When I plugged in a 1/2 and squared it, I got 1/4. When I plugged in a 3/4 and squared it, I got 9/16. And when I plugged in a 1 and I squared it, I got 1. So this is my base times height, base times height, base times height, base times height. I have the area now of these four different rectangles. I can add them all together, and I can get an approximate area underneath the curve of x squared from 0 to 1 of 0.469. But remember, because my graph was increasing and I was using right endpoints, my answer is actually going to be too big. It's going to be an overestimate. Okay? Let's do another one where I'm using left endpoints. The same exact graph, the same exact interval, but now I want to use left endpoints. So I'm going to do four rectangles, base times height, base times height, base times height, base times height. And remember, if I'm going from 0 to 1 and I'm doing four different rectangles, then the base or the width of each of my rectangles is still going to be 1/4. So now all I have to do is figure out the height of these different rectangles. But on this one, they want us to use left endpoints. So if you noticed on my graph, I knew that I was going from 0 to 1. Each one was going to be 1/4 wide. And now I'm going to go from the left endpoint. So I'm going to go from the left of my rectangle, follow it up to my function, and go over. From the left, make sure that that left endpoint touches my function, and go over. From the left, and go over. From the left, and go over. You notice now that my four rectangles are all below my function, and so when I find the area using these four rectangles, my answer is going to be too little. It's going to be an underestimate. And so that always works that way. If my function is increasing and I'm using right endpoints, then my rectangles are always going to be above and it's always going to be an overestimate. If my function is increasing and I'm using left endpoints, then my rectangles are going to be below, and so I'm going to have an underestimate. If my function is decreasing and I use right endpoints, then I know that my estimate is going to be an underestimate. If my function is decreasing and I'm using left endpoints, then I know that I'm going to have an overestimate. That's important to know not only for your homework, but also for your exam. They might not tell you to use left endpoints or right endpoints, but maybe they tell you to find an overestimate or an underestimate. Well, then you've got to change what endpoints you use depending on your function. Okay? All right, let's get back to finding the area of these four rectangles. We have the bases of all 1/4. Now we just have to figure out the heights. So if you notice that the fourth rectangle, the height of this fourth rectangle corresponds when x is 3/4. The height of the third rectangle corresponds when x is 1/2. The height or the y value of my second rectangle is when x is 1/4. And the height, it's really squished, corresponds on my first rectangle when x equals 0. So again, plugging that into my function, I should be able to figure out what the heights are, the y values, when x is 0, when x is 1/4, when x is 1/2, and when x is 3/4. Plugging that into my function of my x squared, I ended up getting these values. Adding them all together, and finding an approximate area underneath that curve of 0.219. But remember, all of my rectangles were below because we were using left endpoints and an increasing function, so my estimate is an underestimate. So the actual area is somewhere between 0.4 and 0.2. We can kind of assume maybe 0.3-ish, right? Well, to get a better estimate, instead of using left endpoints or right endpoints, we can use the midpoints of our rectangles, the middle point. And so we're going to do base times height, base times height, base times height one more time. We're still going to do that same exact graph. We're still going to go from 0 to 1. We're still going to divide it into 4 different rectangles, so each of our rectangles is still 1/4 wide. If I draw a new picture and I want to go with midpoints, I'm going to take this first rectangle, I'm going to think about where the middle is, I'm going to follow it up and draw my rectangle that way. I'm going to take my second rectangle, go from the middle, follow it up, and draw my rectangle as soon as my midpoint hits the function. Same idea for the third one, and same idea for the fourth one. And so now, some of my rectangles are above, and some of them are below. And so this approximation is going to be a little bit better than left or purely right. And so you notice that I knew originally that each of these rectangles were going to be 1/4 wide. But if I go in the middle of 1/4, isn't half of 1/4 1/8? So now I'm going up 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, 8/8, and that's how I can get the new heights of these rectangles using midpoints. I know that the height of my first rectangle corresponds to that middle point when x is 1/8. I know that the height of my second triangle corresponds to when the x is 3/8. I know that the height of my third rectangle corresponds when x is 5/8, and the height of the fourth rectangle corresponds when x is 7/8, the middle of each of those rectangles. I can then plug those numbers into my function of my x squared. I get these values, add them all together, and get an approximate area of 0.328. It's still not exact, but it's better than an overestimate or an underestimate, a left endpoint or a right endpoint. Okay? I do want to say one more thing on your homework, because WebAssign, as you know, is kind of picky. They might give us a function like this parabola and ask us to use overestimates. And so on the example that we just did, we did purely left on part A, purely right on part B, or vice versa, and then purely midpoints. All of the rectangles had the same endpoint, but on WebAssign, they might switch it up on you. So they might say to go from -1 to +1, but only use upper estimates. And so when we do that, we need to make sure that over on the right side of 0, we use right endpoints because those are going to be above. And then if we're on the left side of 0, we need to use left endpoints because those are going to be above. And so it might change depending on where you're at. Because my function is decreasing over here and I want upper estimates, then I want to make sure that I use my left endpoint. And because it's increasing on the other side, I need to switch it and use right endpoints so that all of my rectangles are above. So WebAssign's a little bit tricky. Make sure if it asks you for an upper sum, all of your rectangles are above. So you might have to switch endpoints back and forth depending on your function. I hope that makes sense. Let me know if you have any